Today we shall be going over elementary functions and their interrelationships because they are intimately related to each other. When I say elementary functions, an exaggerated number is 27. A modest number, eventually, these can be reduced to 3. What are these 27? 6 trigonometric functions, 6 hyperbolic functions, then 6 inverse trigonometric functions, and 6 inverse hyperbolic functions. So that's 24 right there. Of course, we have the power function, we have the logarithm, and we have the exponential. Eventually, all these can be reduced to these 3. The oldest function, so old its origins are lost in the mists of time, is the power function. We don't know how it started, but perhaps people wondered about an area, 3 qubits on each side, so 3 times 3, 3 square, or a cistern of 3 qubits on each, so 3 times 3 times 3, 3 cubed, 27 qubit cubes, so on and so forth. So this is basically f of x is x multiplied with itself n times, n being a positive integer. Now, a very trivial property is x to the n times x to the m is x to the n plus m, naturally. Because x multiplied with itself n times, and then x multiplied with itself m times, put side by side, is x multiplied with itself m plus m times. Now, one consequence of this, if we set m equals to 0, x to the n, x to the 0 equals x to the n plus 0. Plus 0 is nonsense, of course. So, x to the 0 is 1. Another thing is if I set m equals to minus n. So, x to the n, then x to the minus n will equal to x to the 0, which I know to be 1. Therefore, x to the minus n is nothing but 1 over x to the n. Another thing would be the possibility of an inverse function. What is f inverse of x? Well, the recipe for an inverse function is this. We write y equals x to the n, my first step. My second step is exchange x and y, x equals y to the n. Then the third step is to solve for y. Y equals x to the 1 over n. Because if I take the power of x to the 1 over n and y to the n to 1 over n, obviously I'll get y to the n over n, y to the 1x. Once we have this, we can generalize f of x as x to the 1 over n to mth power, or x to the m over n. Well, a little bit more generalization f of x equals x to the a. Here, m over n is a rational number, which I'll denote by the set q, while a is a real number. Positives and negatives are both included. Now, what's the most important thing about the power function? Eventually, we would like to express any function of x as a series, in many cases infinite, starting with some power, a negative power if need be all the way to infinity, some coefficients and integer powers of x. So positive or negative. So integer powers of x and integer powers of 1 over x. N is less than minus, n is larger than minus infinity. So power function is essential for everything. It is so essential we don't think much about it. All its algebraic properties are there. We know about when people started thinking about trigonometric functions. So trigonometric functions. This is about 1600 BC, Babylonian mathematics. For a secular way of expressing, let us say the year is minus 1600 Babylonian. There are evidences of this proto-trigonometric functions written on cuneiform tablets, baked clay. Yeah. How do we define trigonometric functions? Well, it depends. A simplest approach would be to have a circle with its center at the origin of our coordinate system xy. Then we have a radius like this. I call this angle alpha, and I define it by its base x and its height y. And of course, the radius is square root of x squared plus y squared. Then we first define cosine alpha, which is x over square root of x squared plus y squared, and sine alpha, which is defined as y over square root of x squared plus y squared. Of course, we define tangent alpha as sine alpha over cosine alpha. There is also cosecant, which is 1 over sine. There is secant, which is 1 over cosine, and cotangent, which is 1 over tangent. That's all the 6. Now, one important thing about this is related to a concept which we call parity in physics. What happens if alpha goes to minus alpha? Namely, I don't go clockwise, but I go counterclockwise. So if alpha goes to minus alpha, what does this imply? Nothing happens to x, but y changes sign. So x goes to x, y goes to minus y. Therefore, sine of minus alpha is minus sine alpha, while cosine of minus alpha is simply cosine alpha. Such functions we call even. Such functions we call odd. We like functions to have these properties because especially when we are doing integrals and between symmetric limits -5 to 5 kind of thing, odd functions do not contribute at all. And even functions also simplify. When you integrate from -5 to 5, the result is actually the integral from 0 to 5 multiplied by 2. So let's remember this because we will want even and odd functions when we come to hyperbolic functions. One thing about these two basic trigonometric functions, as you see, tangent alpha seems to be redundant. It is just the ratio of these two. So our secant, which is 1 over cosine. The thing is, you might ask, if we have these two, who needs all the others? You would be correct, but when we come to their inverse functions, we'll see that tangent or arctangent has a special role that it plays. Okay, back to main stream. One thing that's obvious is cosine square, which is x squared divided by x squared plus y squared, and sine square, which is y squared over x squared plus y squared, added together gives you cosine square alpha plus sine square alpha equals to 1. A crucial identity. Now, let me come up with a simple homework problem. An exercise, simple exercise. I think those exercises are absolutely necessary because the problem with mathematics is it makes sense. So when it makes sense, somebody lectures you on mathematics, it's all very reasonable. Have you understood it? You will not know unless you try it with such exercises. Now, dividing this by, let's say, sine square, you'll get here cotangent squared and nothing from here, and cosecant alpha. There'll be a similar relation. Similar formula. What is this simple formula? Again, if I divide by cosine square, sine square over cosine square will be tangent, and this will be combined with 1 over cosine square, which is secant alpha, a similar formula. So I want two formulas just like this one. Well, perhaps it will not be all pluses, so on and so forth, but it's worth the effort. Now, I will jump a little bit ahead and do something which is something we haven't covered in these lectures. I will talk a little bit about vector analysis. So this is my good old Cartesian coordinate system. Here I have a unit vector u1 hat, which is off from the horizontal direction by an angle alpha, and then there is u2 unit vector, which is off by, which deviates from the horizontal by beta. Now we write u1 as its x component. Since this is a unit vector, its magnitude is 1. So it will be cos alpha, sine alpha, and no z component. u2 hat, on the other hand, will be cos beta, sine beta, no z component. Now, this is not the usual standard notation, but let me demonstrate to you that it's basically the same. Cosine alpha, sine alpha 0, you can express this as cosine alpha 0, 0 plus 0 sine alpha 0 using the basic properties of vectors, namely components are added or subtracted individually. And this thing equals cosine alpha times 1, 0, 0 plus sine alpha times 0, 1, 0. Now, ordinarily, this is what people call the x direction unit vector, and this is what people ordinarily call the y direction unit vector. So it is cosine alpha in the I direction, sine alpha in the j direction, but this is, I think, even better. Now, what is u1 hat dot u2 hat? In one sense, it is the magnitude of this one, 1, the magnitude of this one, again 1, and cosine of the angle between them. So this will be cosine of beta minus alpha. On the other hand, a direct dot product, this thing will equal to cosine alpha cosine beta plus sine alpha sine beta. Now, changing the sign of alpha, we'll see that cosine of beta plus alpha or alpha plus beta equals cos alpha cos beta, because changing the sign of alpha does not make any difference to cosine. We know that. But sine changes sign, so minus sine alpha sine beta. Let's assume we have no problem in taking derivatives. What happens if I take a derivative with respect to alpha? Well, the derivative of cosine will be minus sine. Let us not write the minus. Let's keep that in our minds. So this will be sine of alpha plus beta equals derivative of cosine alpha here is minus sine alpha, another minus sine, so they cancel. So sine alpha cos beta. Then here, if I take the derivative of minus sine alpha, it will be minus cosine alpha. But remember, there is this minus sign, so this is cos alpha sine beta. These are the two crucial formulas for sine and cosine, or in general trigonometric functions of an argument which is a sum. Now, the double angle formulas, namely beta equals to alpha, cos 2 alpha will be cosine square alpha minus sine square alpha. But remember, cosine square plus sine square equals 1. So I can eliminate this cosine square as 1 minus sine square. So 1 minus sine square and another here 1 minus 2 sine square alpha. Similarly, I can eliminate the sine. So this will be 2 cosine square alpha minus 1. Those are the important things which will be useful to us when we study half-angle formulas. Sine 2 alpha is very simple. It is from here, beta equals to alpha case, sine alpha, cos alpha, sine alpha, same thing. So twice sine alpha, cos alpha. Now, for half-angle formulas, I'll say gamma equals to 2 alpha. So cosine 2 alpha becomes cosine gamma equals 1 minus twice sine square alpha, which is gamma over 2. So transposing everything, I get sine gamma over 2 equals square root of 1 minus cosine gamma divided by 2. Homework, show cos gamma over 2 equals square root of 1 plus cosine gamma divided by 2. Another interesting homework is tangent gamma over 2 will equal to this. So one can show that this is 1 minus cosine gamma over sine gamma, or sine gamma over 1 plus cosine gamma. So all these relationships tell us something about the trigonometric functions, which are ancient, 3.5 millennium old, useful in everyday life. But, the real significance comes when one studies Fourier series and such. When one is teaching to administrative science students, freshman math, they react saying that they will not be doing measurements of land, so on and so forth. They don't need the surveying thing, triangulation, so on and so forth. What's the use? Of course, they have no idea that all these business cycles, so on and so forth, when analyzed through Fourier analysis, involve trigonometric functions. Which brings us to inverse trigonometric functions. Basically, it's this. If sine theta equals to x, then theta equals to arc sine x, or inverse sine x. A nice way to visualize this would be to draw a nice triangle, a right triangle with 90 degrees here. Let me call this theta, and I want sine theta to be x. So why not call this 1, and why not call this x? Then how about this phi? Now, theta is arc sine x. But what is cosine phi? Cos phi is also x, the neighboring side divided by hypotenuse. So this tells me that phi equals to arc cos x. So when I add them, theta plus phi, which I know to be 90 degrees, pi over 2 in calculus, equals inverse sine x plus inverse cosine x. Which tells me right away that one of the trigonometric, inverse trigonometric functions here is redundant. If I know inverse sine, then inverse cosine is simply 90 degrees or pi over 2 minus that inverse sine. Now it is very, very important to be able to express inverse trigonometric functions in terms of each other. Let me pose a question first. Cosine inverse x equals arctangent what is my problem? There are two ways of solving this thing. One is geometrical. So, solving for the question mark is tangent of cosine inverse x. So, I draw a nice right triangle. Then this cosine inverse x, let me tentatively call this tangent beta. So this is, let's say, my beta. I want beta to be arc cosine x, or cosine beta equals to x. So how? X 1, and this is 1 minus x squared. Therefore, what is tangent beta? Tangent beta is, just reading from here, is 1 minus x squared divided by x. So my identity, inverse cosine x, equals arctangent 1 minus x squared divided by x. Is this enough? No. We should be able to, this was just a geometric approach. We need to do this by algebra, because there will be cases where when we come to hyperbolic functions, when it will not be possible to work out a geometrical, nice diagrammatical method like this. We should be able to do it by algebra. So again, I say question mark equals tangent of arc cosine x. Now, the only thing I know about arc cosine is cosine of arc cosine x is x. So I write this as sine of cosine inverse x divided by cosine of inverse cosine x. Well, this is trivial, but this is not. What is sine in terms of cosine? Well, let us remember that sine square plus cos square equals to 1. So sine is 1 minus cos square square root. So I'll write this as square root of 1 minus cosine square of inverse cosine x divided by cosine of inverse cosine x. The bottom is very easy, as usual, x, but this is not all that difficult either. 1 minus x square, same result. Inverse cosine x equals inverse tangent of 1 minus x square divided by x. Now, why is this important? Why is this crucial? Nowadays, integral tables are out of fashion. You just write down your question to a Wolfram as an input, and comes out the nice result in a few seconds. But if you have to work with tables, you have to put your integral into a nice form so you'll be able to locate it among the tens of thousands integral. Something like this, integral dx, arctangent 1 minus x square over x. This integral is horrible. All right. The integral of this, horrible. How will you ever find it in a great integral table like Rashtin and Rizik's? Good luck, you won't be able to find it. But on the other hand, so this is impossible. But integral dx, cosine inverse x, which that thing equals to, and this is doable. Now you express inverse cosine as pi over 2 minus inverse sine x, and inverse sine x and dx, you integrate by parts. Right, comes out the answer. Which brings us to a huge and horrible homework problem or an exercise. Let us take the inverse sine function, inverse sine x. This equals to inverse cosine of what? Or inverse tangent of what? Something else, which is inverse cosecant of what? Or inverse secant of what? Or inverse cotangent of what? So 5 question marks here, which should be perhaps done by both methods, by geometry and by algebra. Doing it by algebra and checking by geometry is my recommendation. Are we done? No, because there is inverse cosine x equals to sine inverse question mark, etc. And we'll go all the way to inverse cotangent x equals to. So 5 question marks, and there are 6 lines. So total 30 question marks. This may seem tedious, but it gives you great practice in manipulating trigonometric functions and inverse trigonometric functions. We said that tangent is redundant. It's not necessary because it is nothing but the ratio of two other functions we already know, sine divided by cosine. But on the other hand, the derivatives of inverse sine and inverse cosine are negatives of each other because their sum is constant. On the other hand, the derivative of arctangent is extremely totally different function. Therefore, when it comes to integration methods, all these trigonometric and inverse trigonometric functions are necessary. So that's nearly half, 13 out of 27 functions out of the way. Which brings us to logarithm and exponential. Now, logarithm to base 10 is a very old story, but not as old as minus 1600. In fact, it is plus 1600. So there is more than 3 millennia between the proto-trigonometric functions and the logarithm function. These base 10 logarithms were just for practical calculational purposes. The idea was basically 10 to logarithm of x was x. Similarly, 10 to the logarithm of y was y. So xy, which is 10 to the logarithm of xy by the same argument. But when you multiply them, on the other hand, this thing equals to 10 to the log x plus log y. When we multiply them, same base, powers are added. Because after all, something like this has the same algebraic properties, you know, a base to a power, as the power function. Now, the power is variable and the base is constant versus the power function where the base is variable and the power is constant. The difference becomes important when we are talking about differential properties. For algebraic properties, they are all the same. So the basic thing is logarithm of xy is logarithm of x plus logarithm of y. What's the use of something like this? Well, it facilitates long calculations. Especially in astronomy, you have to deal with two angles for positions, and you need sines and cosines, so on and so forth, horrible multiplications. You look at a nice table, 5-place tables, 7-place tables. They were very fashionable even in my high school days. And you look at the logarithm of x, you look at logarithm of y, simply add them, which is easier than multiplication. Then you again look at the table from the other side and see what is the so-called anti-logarithm of the sum to find the product xy. So multiplying numbers with lots of significant figures were simplified by this thing. The 10, base 10. Why? Well, this is a biological accident. Because we have 10 fingers. How about... okay. 10 fingers. How about horses and computers? Well, they would have base 2. Because a horse has 2 front feet and 1 finger per feet. How about calculus? For reasons which became obvious to Euler, base is E. What's E? E is an irrational, in fact transcendental number, which is approximately 2.7. What it is not all that important. It is actually very easily derived from 1 over the factorials of integers added together. Now, most important thing about base E, it facilitates differentiation. So let's talk about the relationship of the exponential function and the logarithm function. We said e to the ln x was x, just like 10 to the log x is x. How about e to the ln e to the x? Now, if e to the ln something is that thing, so this will be e to the x. So comparing the powers, ln e to the x is x, just like e to the ln x is x. Obviously, ln and exponential are inverse functions of each other. A little bit of a problem is if you decide to work with real numbers, complex analysis came much later. Logarithm of a negative number, this is undefined. In real analysis. So, logarithm is not a very popular function because it doesn't work for all arguments. But still, its algebraic properties are important. Let's go over them. we decided that ln xy was ln x plus ln y. Now let us set y equals to 1. Then ln x equals ln x plus ln 1, which tells me that ln 1 is 0. Not to be confused with ln 0, which is minus infinity from the basic definition here. Another thing is y equals to 1 over x case. So ln 1 equals ln x plus ln 1 over x, which tells me that ln 1 over x is minus ln x. Another thing which is obvious, logarithm of x to some power a is a times ln x. These are the algebraic properties, but the limitation is this works only for positive numbers. E to the x is much nicer. It can take on any argument, so on and so forth. But the problem with that is e to the minus x does not equal to plus or minus either of e to the x. So it is neither even nor odd. What do we do when we have something like this? Well, there is always a way to create an odd and an even function out of an arbitrary function. We define them as cosh x, which is e to the x plus e to the minus x divided by 2, and sinh x is defined as e to the x minus e to the minus x divided by 2. The others, hyperbolic tangent x is sinh x divided by cosh x as expected, and the others are also standard. Now, cosh x is an even function because if you change x into minus x, these two terms are interchanged, and in a sum, commutativity gives you a plus sign. Here, when you change x into minus x, these terms are interchanged, but in a subtraction, you get an overall minus sign, so this is odd. Now, just like we have the hyperbolic functions defined in terms of the exponential function, the reverse is also possible. For example, e to the x is nothing but cosh x plus sinh x, and e to the minus x is nothing but cosh x minus sinh x. I stress this because it is related to an exercise problem I want to give. A crucial thing, for example, is to find cosh of a sum. How do we do this? Well, we can write this as e to the x plus y plus e to the minus x minus y divided by 2. And then perhaps write this as e to the x times e to the y plus e to the minus x times e to the minus y divided by 2. Bring e to the x from here, e to the minus x from here, and do the calculations. And what do we get? We get, do it here, cosh of the sum is cosh x, cosh y plus sinh x, sinh y. So it is like trigonometric functions, but not quite. With trigonometric functions, this would be a minus sign. Now it's plus. Sinh x plus y, on the other hand, is sinh x cosh y plus cosh x sinh y. An interesting problem, which is very important in Einstein's special relativity. That's how we add velocities in special relativity. Express hyperbolic tangent of x plus y in terms of hyperbolic tangent of x and hyperbolic tangent of y. Einstein's law of adding velocities. Now, which brings us to double argument formulas. But before that, we should multiply these two. E to the x times e to the minus x is 1. Here, a sum times a difference is, of course, cosh square x minus sinh square x. So again, as you see, this is very much like the trigonometric identity, but there it was cosine square plus sine square. Now it is cosh square minus sinh square. So another homework exercise would be if one divides by this by cosh square, so there will be a relationship between hyperbolic secant and hyperbolic tangent. And if one divides by sinh square, then there will be hyperbolic cosecant x and hyperbolic cotangent x. These are easy and trivial things. Now, double angle formulas of trigonometric here should be called double argument. Now, sinh is very simple. Sinh 2x equals 2 sinh x cos x. Trivial. Cos 2x is more interesting because this is, as you see, cos square minus sinh square. But using this, we can play with this a little bit. I can eliminate cos square. Cos square x plus sinh square x. Well, I can eliminate cos square, which is 1 plus sinh square, so 1 plus 2 sinh square x. Or I can eliminate sinh square, which is cos square minus 1. So 2 cos square x minus 1. And using these, one can do the half argument formulas. So I simply say 2x equals to y. So I say cos y equals 1 plus 2 sinh square x, which is y over 2. So solving this, sinh y over 2 equals a square root of cos y minus 1 divided by 2. So as an exercise, we may do cos y over 2 and tan y over 2. Very similar to the trigonometric counterparts. Which brings us to inverse hyperbolic functions. Of course, there'll be 6 of those. Inverse cos x, inverse sinh x, inverse tan x, so on and so forth. Again, the main problem is to be able to express one in terms of the other. Just like the previous problem we had in trigonometric functions, let us solve cos inverse x equals inverse hyperbolic tangent of what? There is no simple geometrical construction we can do. We'll have to do this by algebra. But let's isolate the problem. Let's formally solve it. Question mark equals hyperbolic tangent of cosh inverse x. So the important thing is to be able to express hyperbolic tangent in terms of cosh. The first step is easy because hyperbolic tangent is sinh divided by cosh of what? Cosh inverse x, cosh inverse x. The bottom is simple. Cosh of cosh inverse x is simply x. But the top, I have to express sinh in terms of cosh. So how do we express this sinh in terms of cosh? I have cosh square minus sinh square equals to 1, or sinh equals to cosh square minus 1 square root. So I'll go, instead of sinh, a big square root of cosh square of cosh inverse x minus 1 divided by cosh of cosh inverse x. Well, this is a big square root of x square minus 1 divided by x. As I told you, mathematics makes sense. So when you listen to a lecture, everything sounds fine. But do we really understand this? The only check is to be able to do many of these exercises all by yourselves. So you should start sinh inverse x equals to cosh inverse of what, so on and so forth, all the way to hyperbolic cotangent inverse of what. So 5 question marks here, and then cosh inverse of x equals sinh inverse of what, all the way to hyperbolic cotangent, and we go all the way to hyperbolic cotangent inverse x equals to these. So in general, 6 lines, 5 question marks each, 30. One we did. So 29 problems in all. A lot, but when you do them, you master the whole situation. Again, what is the motivation? If you end up with an expression, in this case, let's say integral dx inverse hyperbolic function of x square minus 1 divided by x. This is extremely difficult to find in an integral table. But on the other hand, integral dx cosh inverse of x, this is doable. Integration by parts, and it works.